Oui, c'est ça.
All right, so we'll have our final talk of the day. It's a long distance talk. These used to be very expensive phone calls, but with modern technology, we are very happy to have Zurab to lecture us on forms versus monoidal categories. Thank you, Zurab.
Thank you very much, Izar. It's a great pleasure and great honor, and also I'm so much grateful that it was possible to accommodate long distance participation, especially giving a talk. So thank you very much for that to Andre and to Izar. So the topic of the talk is an interesting phenomenon that I noticed recently, which is part of joint work in progress with Francois van Niekerk. And it has to do with identifying some analogy with the story of monoidal categories, which is a bit unexpected and also not quite explainable. So let me begin with a bit of introduction to monoidal categories, just for the sake of later on drawing the parallelism with this thing that I'm going to explain what it means, the form. So we all know what monoidal categories are, and we also know that there are two standard monoidal structures on a category having binary finite products and sums or coproducts. So we have a monoidal category made out of a Cartesian product, and we have a monoidal category made out of coproduct. But we also have other important operations on objects in a category, specifically in concrete categories, like, for example, tensor product of abelian groups. And so it kind of motivates the idea of having a general structure of adding or multiplying objects, of which these will be examples. And this brings us to the following picture. It will be a picture of concepts. So monoidal category can be seen to decompose into two special types of monoidal categories, the one given by product and the one given by sum. And of course, there are situations when these two structures are the same, when the construction of product and the construction of sum coincide with each other. We call this a byproduct. And then we might want this coincidence to happen throughout the category. And so this way we get a notion of a linear category. This is a category where every two objects have a byproduct. Of course, we want the category to be pointed. Although I must mention that there is a recent paper by Martti Karvonen in Kaye, where he explains how we could define a byproduct without pointedness. So let me just mention this thing here because it's a very fascinating result, and I haven't seen it anywhere before. So the usual conditions are that the top row on this diagram that I drew in the corner is a coproduct, the bottom row is a product, and then we also want these composites to equal identities, the pi 1 iota 1 equal identity of x and pi 2 iota 2 equal identity of y. And then the other conditions, the usual ones to put here, is that the composite across from x to y and across from y to x gives us zero morphisms. But what Martti explains is that That's not necessary. We could also instead just require this to hold. And then somehow magically, in the pointed case, this does coincide with the usual byproduct. And in the non-pointed case, it still allows us to think of this morphism across as a nice zero morphism. It almost behaves like the zero morphism of a pointed category. So I'm just saying that this notion of byproduct doesn't have to be stated in a pointed context, thanks to this definition. But if we want the monoidal structure of product and the monoidal structure of sum to be isomorphic to each other, then the unit for product is the terminal object, the unit for coproduct is the initial object, so we will then force the category to be a pointed category. And in fact, another fascinating fact which I haven't seen anywhere before written down, we can actually define a linear category as a category in which there is a canonical isomorphism between the monoidal structure of product and the monoidal structure of sum. It is not difficult to show that then things do work out and we do actually get byproducts there. Okay, so this is just a very brief story of how we can transition from linear categories to monoidal categories and backwards. And of course, linear categories originate from abelian categories. So I'm going to put another thing on this picture here. Abelian category is a bit more than a linear category. In an abelian category, we also want to have subtractions. Of course, the example of commutative monoids shows that we can have linear categories that are not abelian categories. Now, if we go up this scale, so we generalize from abelian to linear, and then we have this notion of byproduct, which is kind of local linearity, and then it splits up into product and sum, and both of them generalize to one notion of a monoidal category. We can go further up here. Of course, a monoidal category is a category equipped with a monoid structure in a suitable sense, in a suitable two-dimensional sense. So we can say that the idea of a monoidal category further generalizes to a very general idea of a monoid. But then if we think of a monoid itself as an idea coming out from the notion of a category, where we just try to limit the number of objects in the category, then we can attach to this diagram of concepts the notion of a category as well. So, of course, a monoid is the same as a one-object category, and philosophically, we could think of this as a category having few objects, although we don't allow empty amount of objects. Maybe this is just me, or maybe this is widely accepted, or only by some people, but for me, the notion of a monoid kind of captures the algebraic essence of the category. But a category also has geometric essence. So the reason why I say it captures algebraic essence, because it's an algebraic structure. A category is no longer quite an algebraic structure. And the reason for that is because we've got many other objects as well, except that unique object that we have in a monoid. Now, what happens if we do the other way around? What happens if we try to take away the algebraic structure as much as possible, and we just reveal the geometric aspect of a category? So another special case of the concept of a category, which kind of contrasts the notion of a monoid. Then I think we're going to get here. Actually, let's, I mean, since I'm so far and I'm not able to talk to you and so on, maybe it will be nice if we make this talk a bit interactive. So if anyone would like to take a guess what I was going to put here as a kind of geometric trivialization of the concept of a category.
Pre-order posets.
Yes, thank you very much indeed, yes. Posets. So in a poset, we have very few arrows, in the sense that for any two objects, A and B, we have at most one arrow in either direction. So if we have an arrow this way, then we don't have any other arrows in that direction, and also we don't have anything backwards. if we want to allow things backwards, then we get preorders, of course. And whether I write here preorder or poset is not really going to really change the story that I'm trying to tell here. Okay, so then the question is, philosophy, of course, doesn't work always. Sometimes it gives us illusions, but sometimes philosophy works. If we try to ask ourselves, okay, so if a monoid is an algebraic kind of enforcement if a monoidal category is an algebraic enforcement of a category, in the sense that we have a notion of a category, and now we want to make it even more algebraic than it is, and maybe that means we consider a monoid structure over it, so we get a monoidal category. What if we wanted to do the thing on the other side? What would be a posetal enforcement of a category? And there is certainly a kind of standard canonical idea one could have here. Maybe it's a category enriched in posets. And maybe it is indeed. But in order to replicate this picture on the left, I don't think that will work quite, or maybe it will work. And if you think it will, then I would be very much happy to hear about that from you. So instead, I'm going to suggest that instead of considering an enrichment in the category of posets, let's consider what I call a form, so a faithful functor whose fibers are posets. So it's the old idea of Grothendieck to introduce this intuition from topology, the intuition of fibrations. But I don't want this to be a fibration in the most general case. So for every object in the ground category, we have an associated subcategory of the top category. This is the fiber. So this is if this is a functor from a category B to category C, then the fiber is just the inverse image of the object under that functor. So all the arrows that go in here are those that are mapped to the identity functor by F. And so let's require that these fibers are posets. So we can take a simpler example of a functor. So it's a faithful functor that has that property. Of course, topological functors are such, concrete categories are such, and so we have lots of such functors around. Logic makes use of categorical logic makes use of such functors a lot, and so they're very very common objects. And for series of investigations motivated by algebra, I wanted there to be one simple short term for that. So we're using this term form for such a thing, and then might explain also why specifically that term. And so let's think of that as the geometric enforcement of the concept of a category. So we attach a poset above every object. So what we want next is to look for two natural examples of this structure that would kind of mimic how products and sum are two natural examples of a monoidal category. Of course, product is something that kind of ties up with left exactness, with limits, and sums are things that tie up with colimits or right exactness. And so one thing we can definitely find there is the notion of subobject and the notion of quotient. So we could consider the form of subobjects. So this would be fibration of let's say we take the top category to be the category of monomorphisms, and we consider the codomain functor. So that will give us the fibration of when monomorphisms are well behaved in the category, it will give us the fibration of subobjects, and that kind of corresponds to the left exact story. Even though subobject we don't require it necessarily to be an equalizer, but still definition of a monomorphism is type of left exact nature. And the other canonical example of this would be quotient, where we take epimorphisms instead of monomorphisms, and we consider the fibration or obfibration of or bifibration in all good cases of quotients. So these are indeed very important examples, because very often we encounter a situation where we want to work with subobjects, and sometimes we don't even know exactly which subobjects we want to work with. And so we might have a distinguished class of subobjects we want to work with, and then it's kind of meaningful to consider the structure of a form that doesn't specify exactly which subobjects we're interested in. And one of the applications of this story is in the theory of categorical closure operators, where if you look at the development of the theory, eventually less and less was being required of the class of monomorphisms. In most recent papers of Walter Tollen and co-authors of his, you will probably find simply any class M of monomorphisms with a codomain functor. But one can also consider a general form, and the useful notion of closure operator arises there, which we investigated with Marina Gran and Mathieu Duquert-Antoine, where we showed that significant part of the kind of central concepts around closure operators nicely generalize there in that context and give interesting examples. So the need for a form is then in some sense similar to the need for a monoidal category, where we have these two different examples, subobject and quotient, that we want to unify. But just like in the monoidal case, if we only had those two, maybe we wouldn't need monoidal categories so much, because one is just the dual of the other, so we can just work with one. So in the monoidal story, the classical example that motivates the notion is that of a tensor product. And the question is, if on this side there is actually a meaningful form, which we definitely are interested in, but that will be neither given by subobjects nor given by quotients, but given by something else. So that question does arise in order for us to continue this analogy, and I'm going to address that question a bit later. For now, I just want to show you what will happen down here. So the next thing we want to keep the picture symmetric here is to think of a way of combining these two notions, the notion of a subobject and quotient. So a byproduct is a diagram in which is simultaneously a product and a sum. So we're looking for some data which will simultaneously be a subobject and a quotient. And of course, not every product and not every sum is a byproduct. So there is some conditions, right? The object needs to be both, needs to have both universal properties, right? So we don't expect that any subobject will be part of such a pair of subobject quotients. So there will be some conditions that will tie these two together. And so once again, I would like to ask the audience if you can maybe guess what I was planning to put there as a concept, an idea, or a diagram that kind of philosophically we can think of it as something that's simultaneously a subobject and a quotient.
Exact sequence.
Yes, exactly. Yes, thank you very much, Cesar. So it will be exactly a short exact sequence. So, well, we all know what a short exact sequence is, but let me nevertheless emphasize this point here. So in a short exact sequence, we have, on the left side, we have a monomorphism. On the right side, we have an epimorphism. And M is a kernel of E, and E is a co-kernel of M. So in a way, kind of E and M determine each other. So we could have actually just been given M and say that it's a kernel, and then we could take its co-kernel, or the other way around. And so in some sense, this thing is simultaneously a subobject and a quotient. At the same time, we can think of it as the two things coming together. Okay, then the next thing is what to put across as an analogous notion to that of a linear category. And this can be a bit difficult. So in terms of byproducts, a linear category is a category where every two objects have a byproduct. So byproduct is a construction. We take two objects and we build a byproduct out of it. But a short exact sequence is not quite a construction, right? So maybe it's not so clear what to put here if we focus too much on the notion of a short exact sequence. But maybe we can go back to the idea of the form of subobjects and the form of quotients, and thinking of them as some kind of monoidal structures in the parallel universe, where on this side a linear category was the two monoidal structures of product and sum being isomorphic to each other, right? So why don't we say here that what we want here is a structure which has the form of subobjects isomorphic to the form of quotients. So let's make this precise a bit what we mean by that. So if I have a category C in which I have nicely behaved subobjects, I could consider this codomain functor. Of course, if I want the fibers to be posets, I'm going to quotient out this category of monomorphisms a bit, right? But I'm going to ignore that detail now. So let's consider this form of subobjects, form of M subobjects. And let's also consider the form of equotients. Now, it is actually important that these subobjects and quotients do behave well. And somehow the universal property of product and coproduct here on this side of the story kind of tells us that they behave well, even though they don't necessarily need to interact with each other too much. Here, their well behavior is more about their co-interaction than individual properties. So let us consider a setup where we have a proper factorization system obtained by these two classes. So EM gives a proper factorization system. Of course, the standard reference for factorization systems is Kelly and Freight's paper, but proper factorization systems were already defined by Isbell, motivated by MacLean's ideas from the paper on duality for groups. And he called them bicategories before this term was used for a form of two-dimensional category. And the story I know from my father is that Jean Benabou kind of suggested to MacLean or asked his advice or permission about renaming bicategories to have this two-dimensional meaning. And I think that was settled then, and since then we never use term bicategory to denote a category equipped with a proper factorization system. But in Isbell's paper, where proper factorization systems were first defined, a category equipped with a structure is called a bicategory. Okay, so we have these two forms, and let's say that this is an Isbell bicategory. In other words, we have a proper factorization system. And let's require that these two structures are isomorphic to each other, just like we did on the monoidal side to get linear categories. So we will require that there is an isomorphism. So in this case, canonical isomorphism will mean, of course, that the triangle commutes. So it's an isomorphism of fibrations, if these were fibrations. In fact, when we have a proper factorization system, the form of quotients will be a fibration, and the form of subobjects will be an op fibration. And if we have pullback stability and things like that, then it will also be bifibration, both of them. Of course, when they're isomorphic, then because one is one and the other is the other, we automatically get a bifibration. Okay, so what happens here is that if we do require this to be an isomorphism, then we get something very interesting. And this is a result of myself and Thomas Lakehill going back to a few years ago, 2016. We proved the following theorem. In our paper, it's corollary 5.2. So this is a paper called Duality in Non-abelian Algebra 2, DNA 2. We proved there that If we have an Isbell bicategory, so in other words, a category equipped with a proper factorization system, plus the condition that this isomorphism exists, so this form of subobjects is isomorphic to the form of quotients in the sense that I explained on this triangle, commutative triangle, where M is the class of monos from the bicategory structure and E is the class of epis. Then this combination of concepts, Isbell bicategory with that isomorphism of the forms, gives us nothing other than the structure of a Grandis exact category. So this equals without any compromises. So we don't need any further restrictions on the category. It equals Grandis exact category. And so that kind of tells us that what we can put here on the side of linear categories is exact categories. But now I'm going to explain a bit what a Grandis exact category is. So the story here goes back to a paper by Charles Erisman, where he considered this idea of looking at an ideal of null morphisms in a category. There was very soon also a paper by René Lavenholm making use of similar idea. In Australia, Kelly had a similar idea, but he wanted the ideal in the context of an additive category, so it was actually an ideal that was closed under addition as well. So what is Charles Erisman's ideal? It's a class of morphisms that's closed under composition on either side, and we've seen that a lot, especially in the work of Grandis, who really made wonderful use of that and developed basically a large part of homological algebra in that context. There are two books that most of you probably know about that summarize the topic. So given a class N that has the property that if something is in that class, then its composite on either side with any other morphism is also in the class. So that's what an ideal is. We can define the notion of a kernel and co-kernel in a natural way, just in the same way as if we would define it for a pointed category, where the ideal would then be the ideal of actual zero morphisms in the pointed category. And we can require that every morphism decomposes as a co-kernel relative to that ideal n, followed by a kernel. So that's what a Grandis exact category is. It's a category C equipped with an ideal n that has this property that every morphism admits such decomposition. If the category is pointed, it need not be pointed, but if it is pointed, then this notion was already considered by Puppe and Mitchell, I think in parallel, because I don't think they reference each other. It was first Puppe's work and then Mitchell's book. And so in the literature, this thing is often called Puppe exact category or Puppe-Mitchell exact category. And when I learned about these things, I started calling the more general case when the category is not pointed a Grandis exact category, because that means the whole book about these kinds of exact categories that Marco Grandis wrote. Okay, so what we have here is then this exact category in the sense of Marco Grandis, which in the pointed case gives us a Puppe exact category. What about this link with short exact sequences? So a local way of thinking about a linear category is that every two objects admit byproduct. Now the analogy does not quite carry like that, because byproduct here is an operation, whereas short exact sequence is not an operation, it's rather a property. It's a more geometric type of thing. But we can kind of loosen this up a little bit, and we can think of this definition of linear category in terms of byproduct as saying that there are sufficiently many byproducts in the category, and sufficiently many means that any two objects have one. And if we think of it like that, and we want to say that an exact category is a category where there are sufficiently many short exact sequences, then what we're basically saying is that sufficiently many, in the sense that any morphism gives rise to two of them. So one will be the one given by the epimorphism part in the decomposition, and the other one will be the one given by the monomorphism part in the decomposition. So this is how we can reconcile with this thought that perhaps the link between exact category and short exact sequence is similar to the link between linear category and byproduct. So recall that in a Grantis exact category, we do want every morphism to factorize as a normal epimorphism, not just any epimorphism, but a normal one. In other words, a co-kernel of something, followed by a kernel. And so if this is a co-kernel of something, then it will have a kernel as well, and so we get a short exact sequence. And similarly on the other side. All right, so we get this way a nice analogy that continues on. And then the last link that we want to fill here is going back to abelian categories, because after all, abelian category is nothing other than a pointed Grantis exact category which has finite products and sums. And that thing which I think, I mean, it's a well-known fact, of course. If I'm not mistaken, this theorem is due to Tierney. Then, of course, gives us a corollary that an abelian category is the same as a linear category, which is also an exact category. So down here, on this part of the picture, it's just a conjunction of two properties. So we get this nice symmetric, which is not very symmetrically drawn, apologies for that. We get this nice symmetric picture of the analogy between a kind of algebraic type of flavor attached to a category in the form of a monoidal category, and the geometric type of or Posettal type of flavor attached to a category along these lines that we just discussed. Okay, now let's come back to the question of the tensor product. So it is not so clear on this other side, on this wing, why is this abstract notion of a form so necessary if, at the end of the day, all the useful forms are going to be either the subobject forms or the quotient ones. In a similar way, we could have said on this side, if we didn't know about tensor product and other things like that, we could have said, what's the point of a general monoidal category if all of them are just product and sum? And of course, not all of them are just product and sum, and so the question is, on this side, what are the interesting forms that are neither the subobject form nor the quotient form, nor the form of quotients? So to explain that, I will have to remind you of some developments around a notion that goes by the name of a Noetherian form. So what is a Noetherian form? Starting out with this idea that a form generalizes subobjects, we want to be able to do kind of categorical algebra in the context of a general form, where instead of explicit subobjects, we talk about these abstract subobjects, which are things living in the fiber. Okay, why do we want to do that? Well, there is this old problem posed by MacLean in his paper called Duality of Groups, where, for example, the notion of a product is defined for the first time. The problem was to find a self-dual approach to groups. And then he says in that paper that in that paper he will only look at the abelian case, and he proposes some axioms which later, after a bit of evolution, turned into the definition of an abelian category. So the problem for non-abelian groups was left open, and somehow with the development of semi-abelian categories, it became clear that maybe the problem cannot be solved because, I mean, at least not in an elegant way, because I mean, a semi-abelian category is really the context where you have the group-like properties. Semi-abelianness is just a combination of protomodularity in the sense of Dominique Bourne and bar exactness, together with existence of coproducts and pointedness. So the protomodularity there is really the algebraic spirit of the context. And when you have a category that's semi-abelian, and if you want to force some kind of duality there, then you will get an abelian category, because semi-abelian together with dual being semi-abelian gives an abelian category. And so then at some stage, I was learning about the work of Marco Grandis, about his notion of a homological category that's different from the homological category that we find in the book by Bourne and Bourseau. And so I was wondering if these two notions of homological category are kind of can be related to each other. And so this was the line of thoughts that eventually brought me to realizing that we can restate the axioms of a semi-abelian category in such a way that they are now stated about the fibration of subobjects, and then when we do this restatement, then they become self-dual in the sense of this fibration of subobjects. And so I was very excited about this, and so it was a starting point of a long research project which spans across several papers. So the DNA 1, 2, and 3 were supposed to kind of lay down the foundations for this theory to eventually come to the point where one would formulate those axioms, those self-dual axioms, on a form that kind of capture the essence of semi-abelianness. And that was done in the fourth edition of the DNA series, which I wrote together with Amartya Goswami. So that's published in 2019 in Advances. And so there we formulate some axioms on an abstract form, and a Noetherian form is a form satisfying those axioms. What we've got in the context of Noetherian forms is all the isomorphism theorems hold there, the homological diagram lemmas can be proved there, and this is something that still needs to be explored, but I couldn't ever find, I mean, we had lots of discussions about these things with Tim, for instance. We never encountered anything about semi-abelian categories that was expressible purely without any products or coproducts, purely in terms of homomorphisms and subobjects and so on, and that couldn't be generalized to Noetherian forms. And then later, Francois also generalized the theory of products in semi-abelian categories, and he established commutator theory in the context of a Noetherian form in his paper that's published in TAC recently. Anyway, so these Noetherian forms are really useful way of doing abstract algebra as far as homomorphism theorems are concerned. And the precise link with semi-abelian categories is that if the fibration of subobjects is Noetherian, then your category will be semi-abelian. But you can have other Noetherian forms which do not arise from semi-abelian categories, and the question was, can we actually? And so one example is rings with identity. So rings with identity do not give a pointed category, and so they don't form a semi-abelian category, but they do give rise to a Noetherian form. And the Noetherian form, by the way, is not a subobject or quotient form, so it's already one example. But it's kind of obtained from. So what happens there is that we take the category of rings, and we take the forgetful functor to the category of abelian groups, and by keeping the additive structure there. And then there we take the form of subobjects of abelian groups, and we take the pullback. And then this form turns out to be Noetherian, where we have there not just ideals and subrings, but we also have arbitrary additive subgroups of rings as seen as subobjects. So on one hand, it's not quite a subobject form, but on the other hand, it's a bit of a cheating because it's a pullback of a subobject form. Okay, so it's not really a very convincing example of. Not a very convincing analog of something like tensor product, which on this side kind of motivates consideration of general forms. So there is a paper by Dominic Bourne in Advances. I don't remember exactly when it was published, but it's not a recent paper. And it is proved there that the dual of the category of sets is protomodular. And of course, for pointed sets, the dual is semi-abelian. And somehow that means that sets have some kind of algebraic spirit in them, even if it's on the dual side. And so the question was whether the category of sets has a Noetherian form or not. I was quite convinced it doesn't, because that would mean that all the quite technical algebraic type of theorems carry over to sets. And so I asked Francois to prove that it doesn't, to find reasons why it doesn't. And after a few months of research, which I think he carried out during his part of the things he did while he was visiting Belgium, he got stuck, and then eventually we looked at it together, and we managed to prove that there is a Noetherian form for the category of sets. But he did prove that we cannot find any class of subobjects or any class of quotients which will be Noetherian for sets. And so this example that I'm going to explain now is a genuine example of a form that's Noetherian, so that means that all the isomorphism theorems hold for that form and so on. But it's neither a subobject form nor a quotient form. And hence then it kind of motivates one. Indeed, it's interesting to have this general notion of form. Okay, so what is the example there? How do we get a Noetherian form for sets? So it turns out that we actually need to simply borrow an idea from Dominique, specifically his notion of normal monomorphism. If we have I'm going to describe to you what lives in the fiber. So if this is the category of sets, and I take a specific set X, and I look at its fiber, I'm going to describe to you what kind of objects live in the fiber for that form that is neither subobject nor quotient form, but that is nevertheless Noetherian. Okay, so we have a set X, and if I had a subobject, then I would have a subset of this set, right? If I had a quotient, then it would amount to an equivalence relation on the set. But neither of them work. Neither of them give a Noetherian form. So what we need to do is to combine these two things together exactly in the way that one combines in this notion of a normal monomorphism that has a very significant role in the theory of protomodular categories. We take an equivalence relation and a subobject at the same time, but they need to be compatible with each other. So the subobject needs to be a union of equivalence classes. And it also can be empty. So that's one Noetherian form that the category of sets has. And another one, even a better one, that other one will have even better properties. We don't have to take all the equivalence classes. We could just limit ourselves to one. So in that other Noetherian form, the object in the fiber there is given by equivalence relation and a selection of an equivalence class. Or either that or don't select. So we have to keep a choice whether to select or not. And if we do select, we can select any. And of course, if we are working with pointed sets, then an equivalence class will automatically get selected because that will be the one that's the equivalence class of the base point. So that's how we can deal with non-pointedness, just by instead of looking at just equivalence relations, we also want to isolate one equivalence class from it. Okay, so that is the example that answers this question about the analogy in terms of what is an example of a form that's neither subobject nor quotient form. And that brings me to the end of my talk almost. I just will say one more remark. Interestingly, this analogy works at some level, but it also breaks in many different ways. And one of the ways it breaks is that On this side, on this byproduct side, we had the monoidal structures of product and sum coinciding with each other. But for that theorem that I mentioned here, which gave rise to Grande's exact categories, we needed to have an Isbell bicategory structure, and that's a structure. That's not. So it's a factorization system, right? So if I look at this, I was saying that exact categories can be obtained by coincidence of subobjects and quotients, but now for that result, subobjects and quotients need to be organized in a proper factorization, which is not unique. There could be many different proper factorizations. On the other hand, here, products and sums are unique. So that's one way in which the two stories differ, and the question is whether we could bring in this kind of difference on this side as well. And it turns out we can relax a little bit the notion of sum structure, a monoidal structure obtained from sum. Instead of requiring that the universal property holds, we just require that the two maps into the intended coproduct are just jointly epimorphic and dually for product. So the corresponding notion of byproduct we get will be the one where instead of requiring these to be jointly epimorphic and those to be jointly monomorphic, instead of requiring the top to be coproduct and the bottom to be product, we just require the top to be jointly epimorphic and the bottom to be jointly monomorphic. And then such type of generalized linear categories, there are much more of them than ordinary linear categories. For example, any unital category has such byproducts. The usual product has the coproduct inclusions being jointly epimorphic. That's so we get a notion that's really weaker than the usual notion of a linear category. Whereas in this case, we did get some notion that was quite strong. So it's interesting to kind of play around with this analogy and see how one could take some phenomenon that holds on one side and then transfer to the other side and find maybe some new notions and ideas to work with. And I think that kind of brings my talk to the end. I'm also out of time, I guess. Is that right?
Well, you can take another 5 or 10 minutes if you would like to add something.
All right, so just give me a moment, please. Then I'm gonna think just for a second if I wanted to say anything more. I have some notes that I was trying to follow. Yes, maybe I'll add 2 more remarks about about the contrast between these analogies. So another difference between these two stories is that monoidal category is, of course, an internal monoid, right? In a two category of categories, but a form is not an internal poset. So this is not a literal analogy. It's a more. That's why I said it's a bit of philosophical analogy. But nevertheless, it kind of works. Okay. Then the other interesting point is that the isomorphism of the product and the sum on this side forces the category to be pointed, because it forces the unit of the product monoidal structure and the unit of the sum monoidal structure to be equal, so that will be terminal equal initial, so it's a zero object. On the other hand, here, the isomorphism between subobject and quotient forms do not force pointedness. Instead, they reveal an ideal of null morphisms. So something forces pointedness on this side, and the same thing does not quite force pointedness on that side. So at a kind of very broader level, there is an analogy, but then if you start to look carefully, you can also see a bit of distinctions between the two stories. And I think that this is where I should stop then. Thank you very much for listening.
Thank you very much, Zurab. Are there any questions either in Calais or elsewhere in the world?
Oh, yeah. I wanted to ask about this very last thing that you were saying, and if this notion of core fits into the generalization of monoidal category as a by category with just one object, and with the tensor structure given by the decomposition. I mean, are forms exactly some kind of bicategories?
That's a very interesting question. I don't know.
Okay.
But I think it's a very interesting question, yes. I wouldn't expect that they would be necessarily bicategories because, as I said, at a more refined level, there is no analogy, literal analogy at least, but one might have something analogous to bicategory that might fit here, but I don't know what, but it's a very good question. Thank you for that question.
Okay, thanks.
Hello?
Hello? Oui?
Yes. I was most interested by the talk, especially because it lifts questions which we had much thought about with Charles very, very long ago. And in particular, when we introduced the notion of ideal in category. It was in a paper of Charles in 1964, which is reprinted in volume 3-2 of the Œuvre complète, which I have commented. And at that time, the idea was that we wanted to do with categories the things that are generally done with groups for cohomology. It was this the idea. The idea, generally, cohomology, at the basis somewhere there is abelian and so on. And we wanted, because it has always been our hope, to generalize what is done with groups, monoids, and so on, to categories in general. And so it was the reason for which we introduced that. And in the paper of 1964, which was in a colloque de topology in Belgium in 1964, so in part 3-2, effectively, there is a beginning of definition of cohomology in much more general categories than are done generally. And it's something which we have always thought we would like to come back, but we had not time enough to do it at the time. And I had written a little paper in the cahier. I don't remember, it's in the volumes on the colloques we had organized in 1984, after just in honor of Charles, where I indicate some ideas we had begun to find, to do for that, and that we hope to develop, but later on, I have never come back on these questions. So I was most interested by the talk, and I hope very much that you can go in this direction and go further. Thanks very much.
Thank you very much, André. Would it be possible to have some kind of reference to that small paper that you mentioned?
You look on the, if you go to my site, to my site, you'll see that there is a way to go, a link to go to the volumes of Charles, which I have commented and edited long ago. And then you go to this link, and in this link you go to the part 3.1, and it's the paper of with the name cohomology at the beginning, and which is from 1964.
Thank you very much.
And so you have the paper without any problem.
Thank you.
For my own, the paper I have done in 81 probably, it is also in the cahier, but I have not here the exact reference, but I can send it to you. But it's this paper of 64, which I think is most interesting because it takes the idea of cohomology very different from the way generally it is done.
Mm-hmm. Thank you.
Other questions or remarks?
Of
course, yeah.
First, thanks a lot for a very nice talk, Zurab. Just about the question you brought, I forgot your name, but your question that you posed, so what could be a relation between forms and bicategories? If I understand the analogy a little bit, could it be that on the left-hand side, if you take indeed a bicategory with one object, you have a monoidal category, then on the right-hand side, I would expect that you need the two cells to be trivial, like poset-wise. Could it be that something like this gives you a form where you have a bicategory, but on the level of two cells, you don't have just one, but you have either one or none?
Yes. Thank you for saying that. Yes, when that question was asked, something subconscious was triggering, but I couldn't identify what. But what you say now, I think it links more to what I thought maybe. So one has to check this precisely, but something like that should be possible. I think so, yeah. Because this poset structure we have is kind of almost like arrows between identity arrows, something like that, right?
And something else, so your Euclidean forms, and so could you, I'm interested in Hopf algebras, and so we know that the co-commutative Hopf algebras, they form a single Euclidean category, and you said that with your Euclidean forms you can somehow have a more general structure of things that are not Euclidean that can have such a normal Euclidean form. Could it be that for general Hopf algebras you could have such a form, and right, if that happens, can you give some information for Hopf algebras?
That's a very good question. I think at some point with Marino we were thinking about along those lines, but I remember there was an obstacle because these more general Hopf algebras that you have in mind, would they have products and co-products?
Yes, the category of Hopf algebras, non-commutative and co-commutative, they have products and co-products, but they are complicated to compute.
And what about the? So the question is, what form should we pick, right? Whether it should be sub-objects or what it should be. Yeah. So I don't know the answer to that question, but it's an interesting question. Maybe Marino will remember our discussions about it. There was some obstacle I remember, but I might be misremembering. But it's an important question, of course, to look into. So thank you for that question. I cannot answer at this point. Sorry.
May I ask you one thing, Zurab? In this Ethereal forms, do you have the validity of the classical Noether isomorphism theorem?
Yes.
So that is already an obstacle because we don't know if for general algebra, Hopf algebras, the classical Noetherian hold them. Already the first one is a problem here, but the factorization normal equity normal.
So the weird thing about forms is that these theorems obtain different form depending on what form you're considering.
You don't necessarily need classical, if I understand it, you don't necessarily need the classical theorems to come back. Exactness becomes different if you have these forms, right? So you don't necessarily have that kernels and co-kernels are the same as in the GP.
Yeah.
Because you can take a bigger class n of zeros. Right?
Yes, but do your two classes are AP mono or not?
Yes.
That's a problem.
I see.
Okay, but we can speak later.
Other questions or comments? In France or abroad? Non, pas d'autres questions ou commentaires? Ben, merci Zurab.
Thank you very much.
Et merci à tout le monde d'avoir participé sur place ou à distance. Merci aussi aux techniciens qui ont rendu tout cela possible. J'ai trouvé ça très agréable d'avoir un parfum de normalité. Et j'espère que d'ici peu, on pourra faire un cycle avec beaucoup de monde et puis avec des bons repas et avec de la détente. À la prochaine. Au revoir. Goodbye to everyone. Thank you.
Thank you so much to the organizers. Thank you for this opportunity. Thank you very much.
Je voudrais remercier Isar pour le travail remarquable qu'il a fait avec l'organisation de ce congrès hybride, parce que vraiment, je ne m'attendais pas à ce que ce soit aussi bien fait, et de sorte qu'on peut à la fois être loin, près, et j'ai trouvé ça remarquable. Et j'espère que il y aura le même genre de choses qui sera refait plus tard.
On fera de notre mieux, mais c'est le travail de l'informaticien. Moi, j'y suis pour très très peu. Voilà.
Donc, quand même,
au revoir à tout le monde.
Tu t'es suffisamment fatigué pour pouvoir arriver à ça.